in an hour. So just keep that in mind, please. And also, just a little bit of housekeeping here. I'm making several assumptions. I'm going to assume that you're already familiar with the SageMaker dashboard. Actually an overview of SageMaker, and I'm also going to assume you're already familiar with Jupyter notebooks. So I'm not going to spend a lot of time covering those. And I've built in a couple of sessions, if you will, a couple of time slots for questions. When SageMaker goes off to train this data set, I've timed it at about 9 to 10 minutes. So there will be some information I cover there, but also want to take an opportunity to answer questions then. And then when SageMaker deploys the production endpoint, that's about 6 or 7 minutes where we'll do the same thing. So as Chris mentioned, type your questions into there and he'll corral those for us. Oh, and by the way, if you get confused, my name is Chris Burns and the other speaker is Chris Skrinak with a K. So if you want to work at AWS and machine learning, you have to be named Chris. So I don't know if anybody on here is also named Chris, but that's the criteria. It's the #1 criteria. So with that, I'm going to get started. I got a short PowerPoint here. As I said, I want to give you some context around image classification. I don't want to just stand here and read instructions or documentation to you. That doesn't do anybody any good. And the first thing I want to talk about is the data set, which is the most critical component of that. So here's the agenda for the day or for the hour. Lots and lots of stuff to cover. So I'm going to move relatively quickly. This is going to be recorded. So hopefully I don't stutter and stammer too much. So if I say something that you didn't quite understand, it will be recorded. You can come back and review this again. So building a data set, everything is dependent on what I like to call a clean data set. It's a vague term. It's an umbrella term. You could put a lot of different words in there, but clean means no corrupt files. Images are dimensionally consistent, and you have relevant images. I'm going to go over some best practices on putting an image data set together. I also have a bit of source code that's pending legal review. And once that's done, I had hoped it would be done today. It's not. I apologize. I want to share that, and it helps automate the process of putting an image data set together, even if it's just for training purposes. This is not something I would recommend you put into production, but I do recommend that you build your data pipelines around collecting images automatically. Now, some professionals, they insist on 10,000 images per class. A class is, of course, one object that you want to identify. And today we're going to identify 10 what I would call iconic cars, 10 different types of automobiles. Again, it's a smaller data set, but 1 hour. So there you go. And my recommendation is if you're going to do any kind of image classification, you should have about 1,000 images. If you don't have 1,000 images, I think you're going to run into some problems in production. Now we've all heard the phrase about garbage in, garbage out, and it can't be any more true than here in machine learning. So this data, this data set's got to be. I'm sorry, was there a question? Okay, so what I did here, let's talk about the source code real quick. I'm just going to go a real high level overview. It essentially does two primary tasks. One, it goes out to either a Google or a Bing search engine using an API key, and it downloads images about a topic. So what you see here on the screen here is I've just made a list, just a text file of 10 different automobiles. And what the source code does is it takes one of those at a time and it goes out and it tries to find 1,000 images of that subject, that object. Now, obviously, I don't know what I'm going to get when I download this. So there's some steps put in place here to help clean this up. So the first step in building image data set is you want to discard your unusable images. Now, I'm going to preface this with a little bit more information here. This data set was put together specifically for this webinar. So it's very unlikely that you'll encounter a production scenario where you have to do something like this. So again, I want you to take that with a grain of salt. Most image classification situations in a production environment, your customers are already going to have a great deal of images, hopefully. If not, then you would probably assemble those in some more controlled manner. You wouldn't simply go out and do a search on a search engine and collect images. But for today, we did that. And I also wanted to demonstrate the power of the transfer learning option in the image classification algorithm. So when you start with your data set, and we'll go back to that word clean, you want to make sure you discard unusable images. And a great way to find unusable images are going to be the ones that are very, very small in size. They're going to be less than a kilobyte. They're going to be unable to be viewed in your operating system, or they will be unable to be opened in OpenCV. That's a Python library for image manipulation. Now, another aspect of an image is called viewpoint variation. Now, I'm going to be very, very strict with my images on this data set. Now, obviously, that's a car. Everybody can tell that's a car. But for my training purposes, I don't want to use this image because I'm not ready to tell my algorithm that that's a car upside down. I want to make sure that the viewpoint variation from images are all oriented like they would normally be seen. And it'd be very rare that you see a car upside down like that. But technically speaking, we would want our algorithm to identify a car regardless of the angle. So viewpoint variation, very, very important to consider. Second is scale. We can clearly see that this is a picture of a car, but I don't want to train on this because the car, the region of interest that surrounds the car is far too small as is compared to the picture. Now I could crop this out, but there's probably not enough data there. I could crop out the unessentials just to zoom in on the car, but I'd rather just discard this for training purposes and then bring this back later for retraining. Another aspect of image classification is what's called occlusion. You want to make sure that the image is not obstructed by any other obstacles or even shadows. Sometimes that can play an important part in there. And that's a consideration when you're in production and you have outdoor lighting to keep it to consideration. Another one is deformation. Now, I've made a little bit of I don't mean to make light of this accident. Hopefully that person was perfectly fine. But we can see this is a car, but I don't want to train on this for the same reason I didn't want to train on the image that was very, very small in scale. This is not formed correctly. This algorithm is going to generalize on the shape of this is a Prius. That's one of the 10 cars. And so by feeding it this in the training, I'm sort of cheating the algorithm of a good opportunity to understand the correct pattern, the correct generalization of what a Prius looks like. And illumination. Illumination is a hard one to control, simply because the time of day, the lighting in rooms change. And so when you're in production, you want to pay close attention to illumination. There are methods within OpenCV and other image manipulation programs that help you control the lighting and the aspect ratio, brightness and contrast and such. So that might be something that you want to pay extra close attention to when you're putting this into production. And then finally, we have background clutter. Now, obviously, we know that that's a car as humans, but I don't want to train on this picture. There's all my images are RGB. We'll get into color schemes in just a moment, but there's just too much busy background on this image. So I'm gonna kick it out. I don't want to train on this one. All right. So once I have my data set and I've kicked out all the images that I don't want to train on, we want to make sure we also kick out the duplicates. You don't want duplicates, in your training data. You actually don't want duplicates at all. I don't think you should want those in your validation set or your test set. You want to keep duplicates to an absolute minimum. And the good news there is you can create an easy hashing function, And so you get back just a vector there, and you can database that. You can use in-memory database. You can use DynamoDB, whatever you need to use. And when you come across that hash again, you kick out that image. And so what I was able to do is create a data set I tried to go for 1,000 per class. After duplicates and after corrupt images and such, it was all whittled down to about 600 per class. And we'll see just a few minutes there and why the transfer learning is powerful. Now, I haven't mentioned labeling yet because my program does that for me. Labeling it's one of the soul destroying aspects of creating a data set, because sometimes you'll get these images piecemeal. You won't have the opportunity to write some source code that automates this entire process. And my recommendation there is label the folder, the directory that these images are going to be in. Don't worry about labeling each and every image. So if I were to, this is obviously a picture, but if I were to drill down into one of these folders, we'd see it's just eight places of zeros, all the way up to 688 for the image names. Now, what I did with my data set also in this source code is I convert all the images to a standard format, which I chose .jpg. Some of them came down in PNG. Some of them came down in a couple of newer formats, like iPhone's new format, that HEIC or something like that. You want to train on all the same format. OpenCV does a great job of translating those converting those into a standard format. You want to pay attention here to the color depth. That's your RGB value. When you're training, that's very, very important. You don't want to mix black and white with color, or you can, but that first training data set, I want to keep, like I said, very, very strict. And there's also ICC profiles, which are kind of a pain, but something you need to be very cognizant of. PNG files, usually you'll see that it can't convert because ICC profiles. So that's just something to keep in mind. You don't want to discard a lot of good images simply because the ICC profile wasn't converted as well, because that's an easy conversion, simply an extra step. Just a couple more moments on the data set, and then we're going to jump into SageMaker. The last step that my source code does is it resizes all images to a standard dimension. You see in the top picture there that these images came down in all sorts of different formats. I had anything from 32 by 32 all the way up to 16 by 1200. And there's three primary means to right size these: cropping, resizing, and padding. Now I've got an example here where I resized an image, if you the large image down here on the left, and then I padded what would have been just blank space because I wanted to keep that dimension. When you're working with CNNs, now the image classifier, the built-in image classifier, is a ResNet derivative, probably DenseNet by now, and is hopefully going to have inception at some point in the future. But we'll see. We'll see what the roadmap holds for that. So this image has been resized and then padded. And now I use OpenCV there, and it essentially just takes the pixels at the edge and sort of extend those out. So you and I can see that this clearly not a correct picture, but when the kernel, traces over this in the CNN, it's going to just think it's part of the trees. It's going to think the bottom is part of the road. So it's going to blend in nicely as far as our CNN is concerned. And then that last step, unfortunately, is a manual step. I've not found a way to automate this just yet. But it's very quickly. Even though I had thousands of images, I was able to very, very quickly, probably 2 minutes, 3 minutes per class, go through and just simply delete images that were valid images. They were resized properly, but they were irrelevant to me. So here you see the search was for Corvette, and I accidentally got some interior pictures of the Corvette, which is it's correct. But for our training purposes, we wanted to kick those out. All right, so for this example, the built-in classifier, we're using a record IO format. And MXNet provides a tool called im2rec, im2rec.python. It's a Python script that helps you prepare this data set. So it can be downloaded from GitHub. It's a very, very handy tool. It helps you create your training and validation sets as well as the actual binary REC file. I like REC because I can transfer that to other formats. There's a future webinars we're going to have about Onyx, where you can take one platform and convert it to another platform. You can convert MXNet to TensorFlow, you can convert MXNet to Caffe. So you want to be able to make sure that your data set's portable as well. So I chose to not use the JPEG native format. I chose the record IO format. Now, a couple notes here about what I did when I created my training and my validation sets. If you see the command here that I issued for im2rec, I issued the list command and then the recursive command. List means I'm going to make my .lst file. Think of it as a manifest file. It's a list of all the files that's going to go into that data set. And then recursive, because I wanted to iterate through all the subfolders I had in my data set folder. And the subfolders corresponded to one of the 10 classes or one of the 10 automobiles. So the best practices are really all over the place. So I probably shouldn't use the term best practice, but I like to put almost all of my data into training and validation. The testing is going to come later. If I test on 100 images and I'm at 95% accuracy, I can correlate that out to 1,000 images. So I can get a good generalization of what my accuracy is going to be. So I like to put all my images into my training and my validation because that's the only opportunity my algorithm has to generalize. If I keep too much for testing, I might have a super, super, super accurate test result, with plus or minus 1%, but I may have missed an opportunity to get some extra images in there for training. Now, it's a little bit hacky, but what I like to do is I run that im2rec command with the list parameter first on the entire data set. So in my case, I think I had 5,888 pictures. So this picture on the left is a snippet of the top 20 entries in an LST file. The column on the left there is really an index, but one of the things that im2rec does for us is it shuffles those indexes for us, which is very, very handy. So if those numbers seem out of order, that's because they are out of order. So it's not a mystery. The second column is which class that image belongs to. In this case, it's going to be 0 through 9 for our 10 classes. And then finally, we see the actual subdirectory and image that came from. So what I like to do here is I do a little bit of, it's like I said, it's a little hacky. I create an LST file with all my images. Then just with a bit of math, I say, okay, I want 70% for my training, but I want 29% for my validation. So I'm going to just cut and paste with the word editor or text editor, 29% of these, whatever that number is. and I'm going to cut those out into a separate LST file. And then finally, I'm going to take 1% of them and put them in a third LST file for testing. Now, what that does is when I run the command again for IM2rec, it's going to create a REC, a binary file, only for the files in an LST file. So I have my training, I have my validation, and I have my test. Now, here's why I do this. I've worked very hard to eliminate any kind of bias. And if you think there's not human bias in image classification, you'd be remiss. So what I was doing when I was testing this a couple of years ago is I was picking images, and I was subconsciously picking images I knew would have a higher rate of hits. So for instance, in this car data set, I would pick images where there's a super clean profile from the side of the car. And what I wanted sometimes I wanted to see the back of the car. I wanted to see the car from separate angles. So when I let IM2rec shuffle this for me, and I simply just pick 1% of these out of here, they're shuffled. I have no idea what I'm going to get, and it eliminates my opportunity to enter a bias into my test images. And we see here, this is simply, I took my LST files that I'd saved and created the REC files, uploaded the S3, and that's where we're going to jump into SageMaker. So I'm going to end the slideshow here. One moment while I rearrange windows. Okay, so I'm in SageMaker. I'm going to create a new file, a new Jupyter notebook with MXNet Python 3.6. Now, to save time here, I'm going to cut and paste in here as I talk. So the first step is we're going to initialize our execution object. We're going to identify the bucket in S3 that our record sets are in, our data sets. And now just a note about these containers. Obviously, there's 5 containers here, but we're only going to use one. When we built this notebook, we didn't know who was going to be using it, where they're going to be at. So it's just a 2-step process here where we create an array of all the containers available, and then we map it to the region that you're in with your Botto session. So if you see that there's more than one container there, that's what's going on right there. Now, also, this image classification, that's what's telling SageMaker that we're going to use the built-in image classifier. We have a dedicated container image for this algorithm. And again, this is running MXNet. Hopefully I made that clear. So once we've identified the container in our S3 bucket, as well as the algorithm, we're going to begin to set up essentially our hyperparameters. I'm not going to spend a lot of time on this. I'm going to come back and talk about these when we kick off the training job. So if you have any questions about those, go ahead and type those in now, and we'll get back to those in just a couple of minutes. Also, a couple of notes here. See this command in Python? It's just the %%. It's we want to pipe the output to console out essentially. Normally in Python you have to issue a print command. That %% dumps everything here so that we can see the output. And also wall time, just in case we have some Python users that aren't familiar with that. That really means like wall clock time, and 702 milliseconds is the time it took for this entire cell to run. So that's when you see wall time, that's what that means. All right, so I'm going to begin to set up my training job. I'm going to name this. Now, give this a meaningful name here. I've put a little bit of my algorithm in here, 18 layers and 12 epochs, so that we can see that. I easily identify that later because there's going to be an S3 subfolder named after this training job. Now, this is not kicking off the training job. I'm just beginning to set up the parameters that I'm going to pass to SageMaker to do my training. All right, now, identified, or my job name. Now, the training parameters, I'm going to create a Python dictionary here. And I'll walk through some of these very, very briefly. But again, I'm going to come back to these while we're training so we can use that time more wisely. This is a simple dictionary object in Python that contains all the parameters that the training job requires. Here I identify the instance that I'm going to train on. That's the host. How many of those instances I'm going to train on. any extra gigabytes that I might need. Now, I probably don't need that. That's kind of the default 50 because our data set is really maybe 1 gig. Hyperparameters. Now, we're just taking the variables that we've already established up here and placing them here. Now, this is just a best practice coding-wise, so we can come up here and change these variables when we want to rerun this for training. We can set a maximum time we want it to train. I've seen instances where training has sort of gone off the rails and gotten into some kind of cyclical loop where it will just train forever. You certainly don't want that, especially as when you're consuming cloud resources. And then our input channels. This is important. The built-ins are going to look for our training data in a subdirectory of S3 called train. Same goes for validation. So I don't believe I jumped to SageMaker, or I'm sorry, S3, but I'll bring this over really quick. And we see in our S3 folder, we have our training subdirectory with our binary. And then these are some of the test images that I've pre-identified from my test.lst file. So again, still have not kicked off training. We're simply setting up the parameters that are required for training. Now this source code, this will kick off our training job. So we're going to make a call here to SageMaker, and here's where the magic happens: create training job. Now again, if you're not familiar with Python, this double asterisk is really, it's allowing me to pass this entire Python dictionary called training params to this parameter, whereas it could be possible that I would type each parameter at a time in the method call, and this is just simply more efficient. So then this is actually just code that's going to query the training job endpoint, or the training job daemon, if you will, and give us our output. So I'm going to kick this off. This is going to take about 9 minutes. So what I wanted to do in this time is I wanted to go back, check my notes here, and I want to explain what's happening in this training job. So if we go to the SageMaker dashboard and we come in here to training jobs, we see here it's in progress. One of the features of SageMaker is it saves these training jobs so that you can come back and you can rerun these on fresh data sets. I'm sorry, was there a question?
That was just feedback.
Okay, all right. So these training jobs are saved. We can dig into our training job here, and it's going to demonstrate, it's going to reflect to us, recap for us all of our hyperparameters. Now we do have hyperparameter optimization available today. Unfortunately, we're not going to get into that in this 1 hour. That would probably be an entire hour unto itself. So there's some hyperparameter optimization that can be automated. It's very, very handy. If you're working with transfer learning, as we'll see here in a moment, it's very, very powerful. I've been trying to find professional words to describe it, but Friday I was like a kid in a candy store when I had first time I'd used transfer learning myself on a job, and I was expecting to get some very, very low accuracy with a data set I just cobbled together from the internet. But I got some fantastic results that I'll be sharing with you here in a moment. So the training job, what's happening here? We kicked off SageMaker create training job. And it's going now this 10 minutes, but I want to sort of defend SageMaker here because it's not really 10 minutes. It takes 10 minutes to first spin up the EC2 host. In our case, we chose a P3 instance, and then it has to copy down the container for the training with the training parameters on it. So that's another bit of time. And then it actually moves the data from S3 and then begins the training process. So when it's done, we're going to jump into the CloudWatch logs, and it's going to be better outlined there. But the 10 minutes is actually, half of that is probably provisioning time, and the other half is training time. Now remember, SageMaker was built for infinitely sized data sets. We don't use that word accidentally. Infinitely sized, as much data as you can pass to it. So if you imagine a 1 terabyte size data set, the transfer time alone would be measured. Who knows what that's going to be measured in. And training time, given the number of epochs you're going to run, could be a day. So when you're thinking about a few minutes to set up the job, it's really sort of trivial. And what I'm doing here is I'm using SageMaker as a hammer, like a 5-pound sledge to kind of drive a finish nail, if I could use that analogy. So I also wanted to go back and talk about the hyperparameters real quick. And I'll try to keep an eye here on the status of our training job. So hyperparameters. As I mentioned briefly, I don't know if you caught it or not, but the image classifier we use is based on ResNet, or actually DenseNet, probably now. ResNet's about 4 or 5 years old now. DenseNet's a new iteration of that. And you can choose the number of layers that you put in the CNN. Now, the number of layers are going to be different based on your use case. Because we're using transfer learning, which I did forget to point out right here. What I didn't forget to point out, I'll get that in a moment here. Use pre-trained model equals yes. So I'm going with 18 layers because you want to start simple first. When you go deeper, you're going to have, different issues are going to occur. You're going to have, especially with the back propagation, you're going to have I'm not sure what the word. You're going to lose fidelity. So the images that you are going to use for the layers need to match up with the number of layers that you're going to use. The image shape, I'm passing this off to the algorithm. And now 3 represents RGB, 3 color channels, and the 600 by 800, those are the dimensions that my source code chose as the best dimensions so that the most images could be set to that size without losing any data, or as little data as possible. Obviously, we saw in some instances it had to add a bit of padding. Number of training samples, 4122 out of our total of 588. Number of classes, that's how many instances or how many objects I want to identify. In this case, it's just 10. This is just a demo. Now, batch size. So these 3 are probably, obviously, these first 4 you have to have, they're required, but these next 3 are where sort of we'll call it the magic happens. Batch size, epochs, and learning rate. The batch size represents the number of images we're passing into the network at once. We don't want to pass the entire network over to the GPUs at one time. So we break it up into 128. That's the default. That's the default. I got great results with that, so I left it there, but you can play with that batch size. Number of epochs. Each epoch is when the network has gone from beginning to end and then back from end to beginning. So all the way forward and all the way back through the network. And then learning rate is the amount by which we vary our weights and balances for each epoch. So what this means is I'm going to go 12 epochs, and each time I'm going to iterate my learning rate by 0.1%. And what the learning rate is, remember, we're generalizing. I'll show a graph here in just a minute. We're generalizing. We want our error rate to be minimized, and we want it to converge on basically the vector of our image. So if this is simply a mathematical calculation to help us move those weights and those biases. And then the top K2, this is really just going to give us it's going to give us a view of the top 2 accuracies. When we look at the CloudWatch logs, there's going to be a training accuracy and a validation accuracy. And that top K equals 2 means we're just taking the top 2 to check that accuracy. This is probably a safe setting here. I've seen very little need to ever move this into more than 2. And so I'm going to check on our. Okay, so we're still training. I did forget to check the time when I kicked that off, but I want to go now and see if we have any. Chris, do we have any questions?
There we go. Yes, we do. First of all, is IM2Rec exclusively for images, or can you use it on flat files?
You could probably, that's open source code. You could probably alter that code, because what it's going to do is it's going to convert that JPEG or whichever format you do into a binary file. So you might have to play with the method within IM2Rec that actually does the binary conversion, but you could still use all the plumbing around that lets it output an LST file. So that's a question that's kind of a yes with a caveat. Yes, you could, but the caveat is you might have to write a bit of code yourself, because it needs to know how to serialize what's in the file, the original file, out to a .rec file. Got
it. Next up, how many images can IM2Rec handle? I believe it works sequentially.
It does work sequentially, and what it does is it'll ingest either a subdirectory at once or multiple subdirectories at once, and it batches it up into like chunks of 1,000 or 10,000, because that's how it works with the shuffle. And so I don't know what the maximum is. I've used it on, I have a separate data set that I really wanted to use for this demo, but legal told me I wasn't allowed because of copyright issues. So whatever, but it was about 10 gig and had 20,000 images in it. And they were able to, I'm sorry, not 20,000, 200,000 images in it. And IM2Rec was able to shuffle those up just fine on my workstation here, which is a Quad Xeon. So I've not seen any limitations on IM2Rec. Now, obviously, when you get into the millions, you may have some issues there where you may want to chunk that up.
Makes sense.
And when I say chunk it up, I mean use IM2Rec on a subset of your data set, and then another subset, and then maybe combine those LST files. so that you can get that all into one data set for processing.
And do you mind zooming in on your browser just a bit? Control plus once or twice. There we go. Just fill up the screen if you would. Are there any good tricks for handling imbalanced classes in image classification, apart from augmenting the smaller classes?
And I may need some more information here. Imbalanced classes. So when I see imbalanced classes, I'm thinking that maybe, in this case, I might have 3 cars or 4 cars, and then I have a dog. So is that what they mean by imbalanced classes?
Well, I've handled this problem. So let's say you're doing pedestrian detection, and you have 800 images of people crossing the street, but only 20 of them are in a wheelchair, and you want to make sure you get adequate wheelchair representation.
Got it. So augmenting the smaller images, you want to avoid augmentation of your ROI, your region of interest. You want your algorithm to generalize on that pattern as it sees it in the real world. So, I think I need to need more information about this question here, because I'm not sure how you would augment other than maybe supplement, maybe do another query with individuals in wheelchairs and add that to your data set. Maybe these individuals in wheelchairs aren't on the crosswalk. Maybe you've taken them from some other way. So you don't have to use the same source for your image files, as long as the region of interest in the image files that you use is something that might be seen in the real world when you put this into production.
So if you don't mind, so what I've done, if you don't mind an anecdote, Chris.
No.
So what I've done with those images is flipped them, scaled them, because I want to get like 200 of those. And you could potentially transform any image just by ordinary flipping. What I mean is a horizontal flip, scaling and rotating the images. So you could potentially get 8 images out of every single image just by doing those simple OpenCV manipulations.
All right, thank you, Chris. And so our training is done. And before I jump into the next session after training, I did want to go into CloudWatch just for one moment. Head into our logs, training jobs. And we're going to look at our log file from the training session that we just executed. And here we would see everything that would pipe to the console if we're doing this locally. And we can see here that our training accuracy in the first epoch, 49%, not very accurate. But by the time we get down to the 12th, 0.969. Now I had really hoped for a 9.7. It looks like I went 1 epoch too long here. It looks like I began to overfit a little bit here. So you got to play with that. Now, obviously, 0.01% accuracy over the course of 4,100 images is pretty minuscule. But when you put this into production, you're going to want to fight for every inch. You're going to want to fight for every 100,000th of an accuracy. So I wanted to show that this log is here. That's our validation accuracy. And I got that on 4,100 images over the course of 10 classes. So that's where the transfer learning, the power of the transfer learning comes in. And I want to jump right back to the PowerPoint real quick and just talk briefly. So earlier I talked about epochs, I talked about learning rate, and I talked about the number of iterations and the number of epochs. So what happened there to me was really this right here, the overfitting. I went 1 epoch too long. And now this squiggly line here, it's obviously an exaggeration. We want our error rate minimized so that it converges with the path of the standard deviation. Remember, this is SGD. So a CNN, such as ResNet, DenseNet, uses stochastic gradient descent, and that's an iterative process. That's why it's important to make sure that you get a number of epochs in there that are enough to shake out where you're overfitting, where you're underfitting. So what I'm trying to say is you actually want to train until you see an overfitting and then back off. So if I were to do this again, if I were in production, I'd probably back this off 1 epoch, retrain, and review my results. So preparing for this webinar, I played with some different variables. And this is just a quick history of what I did here. And you see in the first 4, I did not use transfer learning on this exact same data set. And you see my validation accuracy is simply miserable, 0.281%. If you think about it, with 10 images, a blind guess has a 10% chance of being accurate. So 0.281 is not very good at all. And what I did here was I flipped it to transfer learning. I did add a couple images when I minimized my test set. So not many, 120 images or whatever. And we see the accuracy here is just skyrocketed. And so I wanted to just take a moment and talk about that, point that out. For me to just grab some images off the internet, throw them into SageMaker with this built-in, and achieve that type of accuracy. And if you look at these times to train, 6 minutes, 7 minutes, 10 minutes, this is all done on the P3. It's $12.24 per hour. So it's 1/10 of that. So for $1.20 per attempt, this is what I was able to get. So if you scale this into a production setting, $100, $1,000. I mean, it's irrelevant. It's really, the cost is so small. It comes out to pennies. All right, so I'm going to jump back into SageMaker so we can get this finished and test, and hopefully the demo gods are on my side today. So what I'm doing here now, oh no, I have to create a unique name for my model. Sorry about that. So the model that I was trying to create was already named. Remember, we keep those models, those endpoint configurations, and those endpoints and those models are stored for us. We can come back and get those at any time. And what it's going to do is going to create, here's that directory, that subdirectory I was telling you about that we use our job name for. And if we go to S3, we're going to find this model.tar.gz file. Now that's going to contain our parameter file and our network file, the .json. So SageMaker is very component based. It's compartmentalized. We don't have to deploy to SageMaker. Obviously, a lot of benefits to deploying to SageMaker, but if we wanted to take that model from S3 and put it into our production processes elsewhere, we could call it with Python code or whatever code we wanted to call just as easily as the SageMaker endpoint calls for us. Now that SageMaker endpoint, it does create a nice API for us to call. So it does a lot of work, creates a container environment for us. Lots and lots of benefits to using the SageMaker endpoint. But what I've done here, or excuse me, what I'm going to do is I'm going to begin to set up the endpoint configuration. Think of an endpoint configuration like an auto-scaling configuration. Auto-scaling configuration is separate from an actual auto-scaling job. So that this is an endpoint configuration. It's going to detail what kind of host I want to host this on, how many of those hosts, and how I want my traffic to be distributed across the instances. So in this case, I have one host, all traffic going to that one host. And this is the command that's actually going to kick off the endpoint. I'm going to kick this off, and I'm going to talk very briefly about what's happening behind the scenes here. Again, this is very similar to the training job. It's going to create an EC2 instance. It's pulling down a container image for my endpoint configuration, and then it's going to deploy that endpoint to that, create an API around it, and then give me back the API that I would need to call to do inference against this model. So this is in process. It's going to take 6 or 7 minutes. So also what I wanted to do here, be mindful of the time. I'll jump back into this PowerPoint real quick, and I'm going to talk about a very common question we get as SAs. How many inferences per second can SageMaker do? And there's not a standard answer for that because there's not a standard model size. There's not a standard, we'll call it image size. We're working with models here. It could very well easily be a text file or a voice file. So I want to draw your attention to this first column here. This was from a presentation I did at reInvent last year. For instance, this VGGNet, I think we ran this on ImageNet, and it was 550 meg. So our network file was 550 meg. So our demo here today, 10 classes, very small. I think it's about 20 meg. So our inferences per second would be very robust if we were to call that, provided that we streamlined our JPEGs that we're passing to it. We chose an instance with adequate network bandwidth. These are all factors that go into that. So you have to be mindful of your model size. You have to be mindful of what you're passing to your model to be inferred against. You have to be mindful of the network bandwidth that you've given your model to use. Those are all factors. So unfortunately, we can't just simply publish a static variable of how many inferences per second can we get against SageMaker. And so hopefully that sheds a little bit of light on that question. And then I have here another, okay, so let's go back. Chris, do we have any new questions?
No new questions, so I'll just put it out to the crowd there. Feel free to chat with us in the chat window. It's on the right side of your screen. If it's collapsed, just click on the little chat cloud. And then I'll just offer, while we're waiting for this to execute, that all of the commands that are in the SageMaker SDK, such as create endpoint, as we've been seeing, and to display the job, those are all available from Bash. So if you have downloaded the AWS CLI, SageMaker is one of the components in that CLI. It's just pip install AWS CLI. So you can type AWS SageMaker and then something like list endpoints or display. What's the command for displaying when the training job is running? Display training jobs. Okay, we have a few more questions coming in. Next up, how would I do this if I wanted to use R instead of Python?
Well, Jupyter Notebook supports R just as well. I guess the question comes in, I'm not an R expert. So when it comes time to deploy an R generated model, you would have to have your own custom container with the necessary code around it to pass the inference object to the R kernel in the container. So just to repeat that in a different way, what SageMaker has done for me is it knows this is done in MXNet. So it has a container pre-built for my endpoint hosting that has all the information I would need in order to call an MXNet endpoint. You would have to recreate that model, that image, that container image around an R generated model. So again, I'm not an R expert, so I know that can be done. I don't know the details as to how that would be done, but that's really I don't want to trivialize it because it's a bit of work, but it does make it relatively simple. You would simply, if we go here back to our Jupyter Notebooks here, these are endpoint pre-built container images for MXNet models endpoint hosting. You would replace this image with your custom image with the code necessary to call an R generated model. So hopefully that answers that question.
That sounds about right. Next up, compression of the model, is that done by SageMaker?
This model is not compressed. The slide I showed that had the compression was part of our presentation at reInvent. We were talking about ML at the edge. So I want to make sure I don't mix those two streams here today.
Is it possible to reuse checkpoints for retraining if the training job failed? So far, retraining has only worked for me when my previous training job was completed.
Well, that might be a feature that is contained in our pre-configured container images for SageMaker. So that's a great question though, because you want to be able to put checkpoints in at your at your discretion rather than at the discretion of the pre-built container. So what I'm going to do, I don't want to give you a wrong answer there because I feel like that's something you should be able to do. So I'm going to take it back to the service team and get a proper answer. So if you could please reach out to me and make sure I know who it was that asked that question, I'll make sure I get you a definitive answer.
Yeah, and I'll just add, everyone on this call, this is an exclusive training session. Everyone on the call is a partner. This offer only went out to partners. Chris and I, as segment specialists, machine learning segment specialists, can go right to the service teams with questions like this, detailed questions. I don't know the answer to this question either, by the way. And we can get responses to you relatively quickly, and that's part of our job, and it's one of the benefits of being in the Amazon Partner Network.
I'm going to query this endpoint. All right, it's in service. So now we can actually get to testing. So I did place 10 or 15 images in S3 from my test.lst file, and all this snippet of code is doing is going out to that S3 bucket and grabbing one of these test images. So just to reiterate, our training did not see this image during training or validation. And I'm going to visualize the image here. And this was a perfect example of what I was talking about. Had I picked my test images manually, I would not have picked this. I think, subconsciously I would have said, it's the back of the car. It's not a good clean profile from the side or front. So I'm not gonna run that. And what I'm going to do now is just put a snippet of code in here that calls that endpoint. I'm simply reading this file off the notebook instance into a byte array, and I'm going to pass it, as the proper content type, x.image, and see what we get. So very quickly came back with a correct identification of Corvette, and it's a 0.974 probability. So that's that's a very high level of confidence. So if I go back here and just grab another file name, let's see. I'm showing my age a little bit, but this was for some reason, I really love to look at this car when I was young. The Gremlin, it's a hideous car. But let's see if it, 0.92%. And I actually had one more. I want to give one more. And this is, again, this kind of speaks to the point I made about not handpicking your test images. Oh, this is also here's a great learning lesson. I developed this data set on a Windows box, and Windows does not care about capitalization. However, S3 does. So Chevelle lower score JPEG is different than Chevelle upper score JPEG. Okay, and this is not the image that I thought it was. So I apologize. Let's see if it's this one. I'll try to talk and type at the same time. Essentially, it was a modified. The car was heavily modified. Here we go. So it is Charger, but we see it's lowered, ground effects, big block, blown engine. And I thought certainly, even with my padding here, certainly the algorithm will miss this one. But we see that the confidence score has been cut in half, but it still identifies it as a Charger. So that's when I think I was messaging Chris, you should see what the transfer learning does. Great stuff. So that's really it. I wanted to make sure that I'm going to check my notes here. I apologize. This is not a scripted webinar. So a little bit of ad hoc talking here on my part, but we still have, we have a full 10 minutes left. I want to make sure if there's any other questions, we get those asked now so that we could try to get, some group learning going on. And that was really all I had today. So, to summarize, I'm showcasing here what I would call the power of this built-in algorithm. Because I use that transfer learning, I had options for hyperparameter optimization. Had that been an issue for me, really I was able to just use my own experience and do 6 or 7 training jobs and guide that training over a few training sessions. But if this were a more complex data set, obviously I'd want to use the tools available to me to handle that hyperparameter optimization.
So Chris, maybe I'll just ask you a few questions, and we'll see if we get any from our audience as well. But what do you think the use case is? I mean, this looks really powerful. I mean, you're identifying car models. I brought up the issue of pedestrian detection before. I mean, what do you think the use cases are for not using the built-in image classifier?
Well, there are use cases for that, and they would really need to be very, very specific. Like, for instance, we had a use case at AWS where a food service company wanted to use computer vision to automatically identify what was on a tray and then bill accordingly. And so they try to take pictures of the contents of the plate and try to identify the food. Now, that's an instance where I don't know if transfer learning would help you. I don't know if the built-in would help you because you would need to amass a data set of very highly detailed pictures of each type of food, and also they couldn't be duplicates. So there's a lot of opportunity there for like augmentation, as you said, rotating, make 8 from 1. So that's probably the only use case I've seen where transfer learning and the built-in was not a good candidate because it really has to be super highly specialized. Oh, it looks like we just got a question. For the scoring, you have it running on a different EC2 instance. Yeah, so I'm currently consuming two billable resources in Amazon SageMaker right now. My notebook instance is still running. So whenever I'm using my notebook instance, obviously I'm going to consume resources there. And I said M series, it's because I knew I'm not doing a lot of resource heavy computing in my Jupyter Notebook. It's a relatively small image. We can even do free tier with the T size instances. My training environment is gone. It tears itself down immediately. So I'm only billed for the amount of time that I trained, which in this case was 9 minutes. And now my endpoint configuration is up and running. So I am being billed for that M4 instance that the SageMaker endpoint is hosted on. So to answer the question, yes, it's a separate EC2 instance. It's within the SageMaker environment, and I chose the M4 size. But because you can save your SageMaker configuration, your endpoint configurations, I can shut that down when it's not in use. So all the normal elasticity configurations and ideas around cloud apply to that.
So I went ahead and posted the SageMaker pricing model. It's really important to understand, especially if you're familiar with Jupyter Notebooks, that the machine and the pricing of running your notebook, as Chris just said, he's running that on an M4. You could even do it on a T2, which is, I think, something like 0.009 cents per hour. All you're doing is hosting a notebook there, right? When you do the training job, that goes off to a completely separate machine. In this case, are P3s, which are the most expensive, but they only run for a few minutes. So you really optimize your billing. Now, deployment of your endpoint at scale, that's an Amazon, a globally accessible endpoint. So the pricing for that is different too. And if you click on the pricing model there, you'll see that the pricing is different in different regions as well.
So here's a question that's just come in. Can I describe how transfer learning differs from other types of ML? So transfer learning, essentially what transfer learning is, to summarize it, I'm using a network, the DenseNet, the built-in algorithm that's already been trained. It's probably been trained on ImageNet. It's probably been trained on a couple of other common data sets that we see today with images. And so it already knows the idea of a pattern. So I guarantee you it's already seen automobiles. And that could be why I'm getting the results that I'm getting. So it's better to start with an algorithm that's already been trained almost in all use cases. So especially these algorithms have been trained on ImageNets, where you have 1,000 different images. There's Caltech with 180 some different classes. So there's these image data sets out there already trained. And to be honest, I really am hard pressed to think of a use case where you would not start with one of those. But the food example was probably the only one I could think of.
Another question here: how feasible is transfer learning across customers?
I think it's absolutely feasible. I think the great thing about this machine learning model is if you're training on a proprietary something with intellectual property, and then you retrain on something else, that IP that was the secret sauce of the first customer is not going to transfer to the second customer. It's not going to accidentally say, hey, I think this is this with this IP attached to it. So I would not be concerned about transfer learning across customers at all. What you want to do, obviously, make sure is that you want to be mindful of multi-tenant endpoints. Each customer would have their own dedicated endpoint.
We're coming up to the top of the hour here, Chris, so we're running out of time and questions. Maybe if you don't mind, just if you have some concluding comments, we can put them in there. And before we do that, I just want to thank everyone for attending here today. There will be a recording of this session available, and also there may be a survey that you might be asked to fill out when you get the email notifying you where the recording is. So obviously, we do seek always to improve our work, what we're doing. Those surveys are the #1 way that we get a chance to do that. So first of all, Chris, you did a phenomenal job here, really impressive stuff. And it looks like we have one more question. Maybe you might want to handle that. and then we're at the top of the hour.
Yeah, so the question here is, have I seen transfer learning with medical images? I have not, but I know it exists. I've not personally seen a use case, but I do know it exists. Medical imaging, now we're getting into HIPAA, we're getting into some privacy, I forget what it's called, patient privacy information. So there's a lot of, the democratization of machine learning sort of ends when it gets into the medical image world, because it's very difficult to share data there. It's very difficult to anonymize patient information. So, but there are a couple of data sets out there that have anonymized it, the patient name. So I know for a fact transfer learning exists. And so, Chris, thank you very much for emceeing for me. I appreciate it. A couple of times you saved me there, got me back on track. Again, I'll say thank you to everybody that joined today. I know our time is super valuable, and there's Monday, lots of stuff to get to. So thank you very much for spending time with me. Here's my email address on the screen. If you have any questions, feel free to reach out to me directly. You're all our partners here. You're all in the ML competency. So I can't wait to see some of the great things that you build with these tools. And that's it. Thanks again for your time.